Good afternoon, children. So today we are going to start with the second part of coordination chemistry. And in the last class, we had already discussed some of the concepts and questions. So today we'll be continuing from that, right? Okay, so there will be some questions on your screen, and what you have to do is you have to pause the screen and try those questions by yourself. So let us see. So the first question on your screen, everyone, pause for a moment and try, everyone. Okay, children, so let us see what is given to us here. Let us read out the question. Given below are two statements, assertion A and reason R. So what is given in the assertion? It's given a cobalt compound is given to us. It is saying that this compound absorbs at lower wavelength of light, whereas the other one absorbs at a higher wavelength. Okay, this one is higher and the above one is lower, right? This is being asked to us. The reason is given that the wavelength of light absorbed depends on the oxidation state of the metal. Now we know that whenever there are electrons, whenever there is unpaired electron and a light falls on it, this electron is going to absorb that light and it's going to go to the higher energy state. Suppose it's here, the electron will jump to a higher energy state on absorbing light. Yes. Okay. So now what wavelength of light, what lambda it is absorbing? It depends upon the energy, or we can say frequency. Whose energy? On the energy of the central metal atom, whatever we're having, or we can say the CFSE, crystal field splitting energy. It will depend on that. Okay. For example, we know that energy or frequency, it is inversely proportional to wavelength. Yeah, it is energy or frequency is inversely proportional to wavelength. So if the energy is higher, the wavelength will be lower, right? This is the key concept here. Okay, so according to that, we'll see the first one. Okay, and what energy are we talking about here? Here we are going to talk about the crystal field splitting energy. We are going to talk about the crystal field splitting energy. How do you know that one has a higher or lower crystal field splitting energy? By looking at their ligand strength. Just give me a minute, children. Okay, so we were talking that the CFSE depends on ligand strength, that it is directly proportional. So higher is the ligand strength, higher will be your crystal field splitting energy. So here we see in both these compounds, NH3 is common, so we'll not look at this. We'll look at water and Cl. Yes, so water has a field strength greater than Cl. Water has a field strength greater than Cl. Hence we can see that this CFSE is going to be greater than the CFSE of Cl. Yes or no, children? Okay. So when the CFSE is higher, can I say the energy is higher here? Energy is more. If the energy is more, the wavelength of absorption is less. Wavelength of absorption is less. Whose is less? Water is less. But here what it is telling us, that for chlorine it is lesser. So this statement is definitely false. Yes. So this statement is definitely false. So wherever true is written, so A is true is written here, this is wrong. A and R are true, this is wrong. A is true, this is wrong. Only one statement you have, and it was very easy if you could guess this. Okay, so from here itself we know that A is going to be the answer, but we are also going to look at R. What it is telling us, it is telling that the wavelength of light absorbed depends upon the oxidation state of the metal ion. Okay, now just now we saw that it is depending upon the lambda. Okay, sorry, it is depending upon the frequency or the energy. And this oxidation state of the metal, the OS of the metal, it affects the CFSE. It affects the CFSE. Okay, generally higher the oxidation state, it is said to have a higher splitting. Okay, so that is what it is telling here, that oxidation state is affecting the CFSE. So we can say that the wavelength of light is also dependent on oxidation state. So this statement is not completely wrong. It has a link to that. It depends on somehow, depends on some manner, right? Okay, so that's why we can say that this statement, children, is true, but this statement is false. And also this is not the correct explanation. Yes, so obviously A is going to be your correct answer. A is going to be your correct answer. So what were the key concepts, the takeaway points from here that we took? We saw that the energy and the wavelength are interrelated, that we know. Yes, and we saw that how your energy is related to CFSE, ligand strength. Okay, then we also saw that the oxidation state is going to affect the wavelength, or basically the CFSE, right? Okay, so these were the takeaway points from here. I hope you all understood. Let us go to the next question. Next question on your screen, everyone. You need to pause it and try. Okay, so let me read out the question for you, children. The question given here is, there is a complex. Okay, what is that complex? NiCl2Br2. It is telling if Ni2 plus is replaced by Pt2 plus. So instead of Ni, you are going to have Pt. Yes. So which of the property gets changed? Okay. So what property is going to change, children? This one, if you know, if you draw or if you see, this is your tetrahedral. Whereas this one adopts dsp2 hybridization, forming square planar complex. I have already told you how to draw the structures and find out the hybridization. So from there you can see that this one is square planar, the other one is hybridization, tetrahedral. So the first thing, the geometry is changing. So this is correct. Okay. Now tetrahedral complexes of Ni, they do not show geometrical isomerism. They have no geometrical isomerism. Yes. But square planar complexes, we know that of the type M, A2, B2, they are going to show your what? Geometrical isomerism. They show geometrical isomerism. Yes or no, children? Yes, square planar shows, so geometrical isomerism is affected. Yes. Then for optical isomerism, these type do not show optical isomerism. The square planar complexes of Pt and the tetrahedral complexes of Ni, they do not show optical isomerism. So this is not going to come. Then is magnetic properties. Definitely we'll say that Ni2 plus and Pt2 plus, they have different electronic configurations, right? They have different electronic configurations, and due to change in electronic configurations, we can say that the magnetic property also changes. right? So the last one is also correct. So can I say that A, B, D? And it is in which option, children? It is in your option number B. Yeah. So only these three things are going to change. Yes. And rest of the following are not going to change. So that is, they both do not have optical isomerism. Yes. Next question on your screen. Try. Okay, children. So here, let's read the question. The magnetic moment is measured in Bohr magneton. We know that the SI unit or the magnetic moment is measured in Bm. The spin only magnetic moment for these two complexes are being asked to us. So we know that, children, when an electron is moving, it can move around the nucleus, right, in the orbits. The electron is moving like this. Yes. Also, the electron has its own axis around which it moves. Electron has its own axis around which it moves. So this is our orbital angular momentum. And it's moving around the axis. Sorry, it's moving around the nucleus. That is our orbital angular momentum. Whereas this is your spin only magnetic moment. Right? Okay. So here only spin only magnetic moment is asked. When we talk of magnetism, we combine both of these, but here sometimes your orbital angular momentum is ignored. Yeah. And we talk about only the spin only magnetic moment, and here that thing is being asked to us. So when that thing is being asked to us, we have a formula for the spin only magnetic moment. It's represented by the symbol mu, which is root over of n into n plus 2, which is root over of n into n plus 2 Bohr magneton. Yes. And what is this n, children? This n is your number of unpaired electrons. Yes, this n is your number of unpaired electrons. Now in these two complexes, let us calculate. Here this is 0, children, so Fe is going to have plus 3. This is x, this is minus 6 equal to minus 3. So here also x equals to plus 3. Now we'll calculate we'll see the electronic configuration in both these cases. The ground state electronic configuration is argon 18, 4s2, 3d6. Yes, for both here Fe3 plus we'll see. If we see in these two cases, children, here for Fe3 plus the electronic configuration will be 3d5. Will be 3d5. Yes. Now for the first case, this H2O is a weak field ligand, whereas this Cn is a strong field ligand. We know that whenever there is a strong field ligand, there is going to be pairing. And whenever there is a weak field ligand, there is no pairing. Yes. So the first case is for the case of water. The second case is for the case of cyanide. So if we see in the case of water, there will be no pairing, and as usual you'll write that way. It is 1, 2, 3, 4, 5. Yes. Okay. And in the cyanide case, you have 1, 2, 3, 4, 5. Is it like this? No. There will be pairing. There will be pairing. Yes. So there will be pairing. If there is pairing, we're going to write it like this. So in both the cases, we see there are some unpaired electrons. Here n equals to 5, whereas here n equals to 1. Now we see that for the first case, n is more. So mu depends on n. Mu depends on n. Yes or no, children? So when n is more, so mu1, if it is for this one, this is going to be mu2. As n is more, so I can say that mu1 is going to be greater than mu2. Yes, mu1 is going to be greater than mu2. So here you see that mu1 is less. So this is wrong. Yes, it cannot be same because it is different. Now here you see this cannot be, again this one is greater. Okay, so you have to check for this both. You have to check for this both. Yes, so let us see in this case what's happening. If I write n is 5 into 5 plus 2 root over, this is going to be 5 into 7. This is going to be root over of 35. Now don't sit down and find out the root of 35. Okay, we know that root over of 36 is 6. So obviously 35 will be somewhere around 5.9 or 5.98, something like that. So it is present only in one option, that is option number B. So option B is going to be your correct answer. If you want to check for the other one also, you can check. So mu is equal to root over of 1 into 1 plus 2. So that is going to be root over of 3. Root over of 4 is 2. So obviously root over of 3 will be 1.8 or 1.9, something like that. So this is 1.732. So it is same for both. Now we know that for B, obviously you are going to calculate for the first one, because in A and B, these two options are same. So you're not going to calculate for that. You're going to calculate for only one. Yes. Okay. So if you have this formula in mind, you can calculate in mind itself. Like 5 into 5 plus 2 is 35, root over of 35, which is near to 36, and it's going to be option number B. Right. So option B is going to be your correct answer. And I hope nobody has any kind of doubt in this question. Yes. So we are done with our third question. Let us move on to the fourth question. Yeah, one question on isomerism as well. So let us see what's given here. Okay, children, let us see. Total number of stereoisomers for this complex. So what is given here, we'll see. Now can you tell me what kind of complex is this? Whether it is a tetrahedral complex or octahedral complex or square planar complex? As we can see, this is a octahedral complex. Why? We know that this one has a density of 2. Density equals to a total of 2 ligands. So there is 4, this is 1, and this is 1. So this is going to be your octahedral complex. Now for this compound, can I say that definitely this is going to show your geometrical isomerism? Yes, geometrical isomerism, because this is of the type metal LL whole twice AB. Yes, this is that type, and these kind of ligands, children, they show your geometrical isomerism. Like we see, yeah. So this, children, is a trans isomer. If we look for the other one, yeah. So this one, children, is your cis. And now this has a plane of symmetry, right? This has a plane of symmetry. If we pass a line through this, we see that this has a plane of symmetry. So there will be no stereoisomer. No stereoisomer for this. Yes, but these compound children, this is going to have this form is going to have stereoisomer, and it is going to exhibit in the form of D and L forms. D and L form. So total, how many isomers, children? We are going to have a total of 3. 3 isomers. Yes. Okay, we are going to have 3 isomers. Yes or no, children? So if you see the answer, the total number of isomers is going to be 3. Okay. Yes. Moving on to the next question, children. This is the 5th question, right? Okay. So everyone, pause your screen. We have talked about magnetism. Think a little bit more, and I think you will be able to find it. Until then, let me see if you have any doubts, and we'll see. Okay. Were you all able to find the answer, children? No answers? Okay. So let us see what it is being talked about here. So it is saying that some complexes are given here. Out of this, which one will exhibit maximum attraction when a magnetic field is applied? So we can talk about that there is interaction between the magnetic field, interaction of electrons with magnetic field. So whenever there are more unpaired electrons, more number of unpaired electrons, there will be maximum attraction. Yes, because we know that whenever there is more number of electrons, unpaired electrons, the compounds are paramagnetic. When it is paired, it is diamagnetic. And paramagnetic itself means it is strongly attracted by the magnetic field. Yes, it means strongly attracted by the magnetic field. Okay, so we'll see that which one has a higher attraction. So as you can see, children, here in case of this cobalt, this is not going to have the highest. Why is it not going to have the highest? Because this one, children, this is your strong ligand. Whenever there is strong ligand, it is going to cause pairing. So when there is pairing, lesser unpaired electrons. So we can say less attraction. Okay. Similarly, for Zn2 plus, if you see, this is also not going to be the answer, because if you know the electronic configuration of zinc, it is argon 4s2 3d10. So again, if you remove 2 electrons, because this is having 0, so x equals to plus 2 here. Even after you remove 2 electrons from here, it is going to have an electronic configuration of 3d10, which is fulfilled. So this is diamagnetic. So this is also not going to be there. So this is also not the answer. Now we'll be confused between this both, right? Now if we see children, nickel and cobalt. Here also the oxidation state is +2. Here also the oxidation state is +2. Yes. Now, if we see their number of electrons, so we know that it is ferrous, cobalt, nickel. So 26, 27 and atomic number 28. So your nickel is 28. So this is argon 18, 4s2, 3d8. Yes. Again, your cobalt is argon 18, 4s2, 3d7. Now, if we see at this, +2 oxidation state, so these two electrons are going to be, it is going to have 3d8 and this is going to have 3d7. So 1, 2, 3, 4, 5, 6, 7, 8. So 2 unpaired electrons. Yeah. 1, 2, 3, 4, 5, 6, 7. So this is going to have 3 unpaired electrons. So now more the number of unpaired electrons, so higher is going to be the attraction. So which one is going to have higher, children? Obviously cobalt complex is going to have a higher attraction, right? So option B is going to be the correct answer. Option B is going to be the correct answer. Yes. Okay. I hope everyone understood this. Let us move on to the next question. Next question on your screen, everyone. Try. Okay. So what is the question given here, children? It is given here that which complex dissolves in water? So there are 4 complexes given to you. So out of these complex, which one dissolves in water? It is being asked to us. So FeNCN here, you have to look at the complex here mostly. So you see in all these cases, children, in all these 3 cases, there is a very strong bond inside the complex, okay, between the central metal atom and the ligands. They're not going to dissolve. Although the potassium, ammonium, they are all water soluble, but whatever is present inside the complex, that is insoluble. So hence these 3, they are not. But here if you see, you're both OH, OAC, they can form hydrogen bonding with water. So from here, you can say that this compound is going to form, or it is going to dissolve in water because it can form hydrogen bonding. So which one is going to be the correct answer, children? Option D is going to be the correct answer. Okay. So let us see the reason also why. We'll highlight the important points here. The complex is composed of iron atoms. So we are having obviously iron atoms. This is your iron atom. It is coordinated with hydroxide and acetate ligands. Yes. We have OH, we have OAC. And a chloride counter ion. Yes. Hydroxide and acetate. They're polar. Yes. Because they can develop polarities like delta plus and delta minus. And they can form hydrogen bonds with water molecules. So whenever there is water molecules, they can form hydrogen bonding. Yes. So that is a key factor for solubility. Also this chloride ion is also soluble in water. So the presence of these ions, okay, so it's making the complex favorable for dissolving in water, okay children. Yes. Okay, so I hope everyone understood this. Yes. Okay, next question. Okay, sure. So let us see what are we talking about here. Here the question is the set which does not have ambidentate ligand. So basically here we are talking about ambidentates. First of all, we'll see denticity of ligand. So what is denticity of ligands, children? Considering some ions. Okay, so here, suppose we are attaching a metal atom here. It is going to be attached through one side only. Yes? Okay. Now, if I attach here, it can be attached through oxygen only. If I attach here, it is going to be attached to nitrogen only, right? That is called as denticity, which is the number of donor atoms with which the CMA is linked. Yes, that is called as the denticity. Now, in all these cases, it is 1. If you see here, it is 2. Through 2 sides it can link. Here, there are 2 donor sites, but at once, the linkage is possible only through 1, either through oxygen or through nitrogen. So, where there are 2 donor sites, but at one time, only one donor atom is linked. Yes, so that is called as your ambidentate ligand. So now look and see and tell me, children, out of the following options, where don't you have an ambidentate ligand? If you understood from here, it's very easy for you to answer even if you don't know so many things, because you know that. You can see water here, right? Water has only one donor side. See how easy questions you're getting. So this is unidentate ligand. So obviously this is going to be the answer, because here we don't have all, these are not ambidentate ligand, right? So this is going to be your answer. But let us look at the other ones as well. Talking about C2O4, that is oxalato, right? So it is COO minus, COO minus. So it can link through these 2 oxygen. Yeah, so this can be ambidentate. Yes. NO2 I've already discussed. NCS, or it can be SCN, thiocyanato N, thiocyanato S. So either through nitrogen or through sulfur. So here also it is possible. Yes. This is possible. Ethylene diamine, I had drawn the structure. This was the structure of ethylene diamine. This is a didentate ligand. So here also ambidenticity is possible, right? So this is also, but this one was not possible, right? NO2 we have discussed, this we have discussed. EDT, ethylene diamine tetraacetate, right? Ethylene diamine tetraacetate. So this, children, is a hexadentate ligand. This, children, is a hexadentate ligand. Okay, so being an hexadentate ligand, so we'll see the structure of this. So we know that ethylene means 2 carbons. Yes or no? CH2, CH2. This is diamine. So and nitrogen can form how many bonds, children? Nitrogen can form how many bonds? 3 bonds. So 2 are remaining. That is a tetraacetate. Yes, this is going to be CH2, children. Why? Because already one bond it is making. So this is, children, your ethylene diamine tetraacetate. Yes, okay. This is your EDTA. Okay, so this is how your EDTA is going to form bonds, and as you can see, there are 2 oxygen here, 2 oxygen, so total of 4 oxygen. Nitrogen is also there, so total of 2 nitrogen, so you're going to have 6 sites. Yes, you're having 6 sites, right? Okay. Next question. Which part of the complex has a possibility to exist as meridional isomer? So if you have some idea about facial and mer isomer, you'll be able to do this question. So direct from NCERT. Try this. Okay. So here we are talking about meridional isomer. So we know that this is one kind of isomerism which is exhibited by a compound which has M A3B3, right? Where A and B are your, and this is an octahedral complex. The compounds of these type exhibit your what, children? Facial and mer isomers. So is this? No, this is a what? Tetrahedral complex. This is octahedral, okay, but it is LL whole twice A2. No, yes, there. This one is LL whole thrice octahedral. This is not under that category. Here, if you see, M is there, A3, B3, and NH3 and NO2 both are unidentate. So can I say, children, this one is going to be your meridional isomer. Yeah. So if we see, this one is going to be your answer. Now we'll see what exactly your meridional isomerism is. So it is a geometrical isomerism, children. It is found in octahedral complexes with 3 identical ligands occupy a meridian plane. Okay, so at least 3 identical bidentate or monodentate ligands are required. So if you see, this is your mer isomer. Yes, it's kind of like trans, right? This is kind of like cis. So these are 3 facial, they lie on one face. Okay, and here only just 2 are there and 1 more is here. So this is your mer isomer. Okay. Okay. Now again, next question on your screen. Everyone needs to try this and let me know what is the answer. Okay, children, I hope you all would have got the answer, but let us discuss. So correct. So it's giving about the increasing order, right? Now, can you see, children, that cyanide out of A or E, someone is going to have the least. Someone is going to have the least. And who is that going to be? The one which has a strong ligand. So both are having strong ligand. Okay. Second is which has a higher atomic number, because when the atomic number is higher than what your chromium or manganese, after that your pairing starts, right? Because until now you would have known that for manganese and from chromium you are having completely filled, half filled d orbitals, right? So after that when the electron increases, so you're going to have paired ones. So this is going to have the highest number of paired electrons. Yes. So wherever A is there in the option, can you eliminate that? Yes, you have eliminated that. Now here you see E is there, here also E is there. Now if we find out whether between B and C, which one has a higher, then we can know. So now if we see for this both, children, again, now the same thing. Here it is also having a +3 oxidation state. Here also it is having a +3 oxidation state. And here F is there. What is there? F is there. F is a weak field ligand. F is a weak field ligand. So as F is a weak field ligand, it is not going to cause pairing. It is not going to cause pairing. Yes or no, children? If it is not going to cause pairing, then there it will be more number of unpaired electrons, which has a lower atomic number. So we know that Fe has 26. This has 27. So obviously 6 is going to have higher unpaired electrons. Yes. So for instance, we can see this also. So option your D is going to be the correct answer. Let us check. Okay, yes, D is the correct answer. Yes, okay. So if we see here, so we have Fe 3 plus. Here we have cobalt 3 plus. So this is argon 18 4s2 3d6. This is argon 18 4s2 3d7. So after in the +3 oxidation state, it is D5 and this is D6. So D5 from here you know that it is obviously 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 5 unpaired electrons. But here the sixth one is going to be paired, right? So obviously this Fe is going to have your higher number of unpaired electrons. So when you get these type of questions, these are all asked in 2023. Last class we had discussed about your 2024 questions. Yes or no, children? So when you have these kind of questions, no children, just use your common sense. You're not going to sit and find out the electronic configurations of everything. Okay, so you need to know that this one is your strong field, this one is strong field. So out of these someone is going to have more pairing. Who is going to have more pairing? Both are strong fields, obviously pairing is same in both the cases, but here we know that when the atomic number increases, the pairing is the number of electrons are going to be paired more after chromium and your what, manganese. So Fe and nickel. So from here we find out nickel is having higher atomic number. So obviously E is going to be there. So A and A got cancelled that way. Then we looked at the last one, that here lower one will have less pairing. So Fe is going to be there. So this will hardly take you a 30 seconds to solve this question, right? Okay. Moving on to the next question, children. Okay, try this everyone. Now, coming to the question, children, coming to the question here, we have the octahedral diamagnetic low spin complex among the following. So first of all, the compound has to be octahedral. Yes, it should be diamagnetic. Also, it should have a low spin. Octahedral means 6, coordination number should be 6. So now you can see that in this compound, coordination number is not 6. So this got cancelled. Yes. Now, diamagnetic. Diamagnetic means there has to be pairing. Means strong or moderately strong ligand is required. Low spin again is pairing. Now, very easy. See here, weak field ligand, weak field ligand. So this is not possible. This is not possible. Only one option is possible for you. And what is that option, children? That option is going to be this one, right? Easy. These were all asked in 2023 shifts. So you see, you need to have some basic idea just, okay? So octahedral, this one got cancelled because this is tetrahedral. Okay, and these children, they are definitely going to be paramagnetic. Yeah, why are they going to be paramagnetic? Because there will be no pairing. And why is there going to be no pairing, children? Because your chlorine and F, we know that they are weak field ligand. And only one. And here NH3 is a moderately strong ligand, but I told you that cobalt in +3 oxidation state, whenever there is a moderately strong ligand like NH3 or water, they are going to act as your strong field ligand. They are going to act as the strong field ligand. Yes, I hope this much is clear. Next question. Again, the same bit of same type of question. Try this. So now let us see, children. The question that is being asked here is, which is octahedral, right? So all of these are octahedral. Diamagnetic means there will be pairing. Can I say this will not be? This will not be. Yes. And most stable. Okay. Most stable. Now see, from here the word most stable is one which has a higher CFSE. When CFSE is higher, children, stability is higher. Why? Because when there is more CFSE, there will be pairing. Yes. And when there is pairing, we know that pairing causes stability. Pairing causes stability, right? Okay. Now, how will you get a higher CFSE? When there is a stronger ligand. Field ligand. Now, did I need to solve this? Because here I saw that there will be no pairing, here there will be no pairing. Now, nickel in this state, this is not going to be a very strong ligand because this nickel is +2 oxidation state here. And here if you see, children, this is going to be +3 oxidation state. And again, this is a very strong ligand as compared to NH3. So whenever there is a strong ligand, it is going to cause pairing. It is going to be more stable. So that's why we can say, children, could I have directly written this as the answer, that this is going to be the answer? Yes, would I have directly said that this is going to be the answer? So that is how you approach the questions, right? Yes or no, children? Okay, so that's it for today. And with this, your coordination chemistry is over. In the next class, we are going to start with a new chapter. Okay, so I hope you are going to revise this and come for the next class. Okay, so until then, take care, children. Bye bye.